arctan of x, we will be able to explicitly build its power series expansion in 11.10. But right now, we don't have those tools. And so instead, we're going to use what we already know about arctan. And here's what I know about arctan. I know that it is the antiderivative of this lovely function 1 over 1 plus x squared dx. Okay. So because it's an antiderivative of 1 over 1 plus x squared, and 1 over 1 plus x squared is close enough to one of our common power series functions, we're essentially going to do what we did here in example 3. In fact, I kind of wish example 3 were just 1 over 1 plus x squared, but we're going to do exactly this idea. So let's find a power series expansion for 1 over 1 plus x squared because it kind of looks like 1 over 1 minus x. We have to do a little trickery to make it look like that, but there it is. So this looks like 1 over 1 minus negative x squared. So in the power series expansion for 1 over 1 minus x, we're going to replace x with a negative x squared. So this is 1 plus, this is the power series expansion for 1 over 1 minus just x. But everywhere I had x in the original series, I'm going to put my negative x squared there. Okay, and this goes on. All right. Now, sorry, I'm probably being super annoying about this, but I just can't stress it enough. What do I mean equals? What do I mean here? Okay. In fact, what's the domain of your original function? Are there any values for x where this is undefined? No, this thing's domain is all real numbers. There's no issue with what you can plug into x. Does that mean that the power series you find for it will always give you the right output for that function? No. So this thing has an interval of convergence. And what is its interval of convergence? Well, this series ends up looking like once we reduce it down, we end up getting, I believe it's alternating. Yeah, what do we get? Yeah, it's alternating. If we start at 1 and go to infinity, our first term will be negative 1 to the n minus 1, x to the 2 times n minus 1, because we've got even powers of x. All right, so this is an alternating series, and moreover, you can also think of it as a geometric series by just squishing the negative 1 in with the x, so it's geometric. Okay, so this series can be reduced as negative x squared to the n minus 1 power. So we basically just combined the negative 1 and the x squared to both be to the common power of n minus 1. Okay, so this is geometric and it has common ratio negative x squared. So for it to converge, it needs the common ratio to have magnitude less than 1. Well, when is the magnitude of minus x squared less than 1? It's less than 1 if x squared is less than 1, which is valid if x is less than 1. Now, we could still test when x equals 1, and in fact, what do you guys think? If x equals 1, does this converge? So I will let you discuss this, but the radius of convergence is 1, and it's possible that we have any one of these 3 options for the actual interval of convergence, any one of these 4 options, and I'll let you explore which one of these 4 intervals is the interval of convergence. But the point is that it's strictly smaller than the domain of the original function. All right, now that we've got a power series expansion for 1 over 1 plus x squared, our theorem says for those values, I can anti-differentiate the power series term by term. So when I take this antiderivative of the power series term by term, when I say equals, we just have to keep in mind, hey, oops, and I need my integral symbol in here, antiderivative dx. That purple is only valid for x values whose magnitudes are less than 1, and you might need to check at 1 and -1. Okay, so if we anti-differentiate term by term that series, I'll go ahead and pull the constant -1 to the n-1 out, and then if we add 1 to the power of x, we have 2 to the n-2, 2n-2 is the power. Adding 1 to that gives us 2n-1, and then we need to divide by that new power. Okay, great. So this equality is true only for values of x between -1 and 1. And now I'm going to go to my little Desmos demonstration here, just so you can see. Okay, so on the left here, you can see that we have exactly g of x is the power series we just derived. And if we look at the graph of arctan, so arctan is the red graph, and g of x is the blue graph. And so as we increase n, you can see that it fits to arctan tighter and tighter and tighter, only for x values between -1 and 1. So here, when we get off to -1 and 1, our power series is not very close to arctan. But if we increase the number of series terms that we're going to use, it gets tighter and tighter, but it still never, ever, ever, ever gets close to arctan after 1 and before -1. So the interval of convergence is -1 to 1. All right, great. Hopefully that visual assisted you. Okay, now, what we want to do is we want to actually use the fifth term in that series, so the fifth partial sum, to approximate the value of arctan of 1/2. So we're going to use the series we just derived. Let me copy it here. From j equals 1 to 5 of -1 to the j-1, x to the 2j-1, all over 2j-1. Okay, at x equals 0.5, because this is going to be a good approximation of arctan of 0.5, simply because this x value lives inside the interval of convergence. I should say is inside the interval of convergence. If I asked you to approximate arctan of 1.5, this would not be a valid thing to do. Okie doke. So arctan of 0.5 can be approximated using this power series where we evaluate x at 0.5. And I don't really want to write all these out, so I'll just tell you that this value, this power series value, comes out to be 0.46863. Okay, and the actual value of arctan of 0.5 is 0.468647 or something, so I'll just put 5 here. But you can see how good of an approximation this actually is. It's pretty good. Okay, last example, and by the way, this picture is basically the Desmos that I just showed you. Okay, last problem, example 5. So this problem, to be honest, I did it a really hard way. So I did a partial fraction decomposition, which, hey, you know what? That's the first thing that came to me. And I'll switch pages here so you can actually see it. It's also on the solutions PDF that you'll have access to. But I did a partial fraction decomposition for x to the fourth all over 1 minus x squared quantity squared. And I ended up getting it to be 1 plus, let me scroll down here, negative 3/4 over 1 minus x plus positive 1/4 over 1 minus x squared plus negative 3/4 over 1 plus x plus 1 over 4 all over 1 plus x quantity squared. So this took forever, and I guess you'll just see it on the solutions. But why did I do that? Well, because each of these guys, I knew my denominators would be 1 minus x squared, 1 plus x, and 1 plus x quantity squared. And those are all similar to our common power series function, 1 over 1 minus x. So I knew I was going to use this series to change all 4 of these little partial fraction decomposition pieces. So now that we have this partial fraction decomposition, and again, you can go and look at the solutions and just be glad that this isn't the best way to go about this problem because it's a super long fraction decomposition. But now that we have this, we can do a couple things. Let me label each piece of our partial fraction decomposition as A, B, C, and D. And A is just a constant times, it's just a constant times this familiar series that we've been working with. So that's just negative 3/4 times 1 plus x squared plus x cubed, etc. B, let's go to C next. So C is also just a constant times not 1 over 1 minus x, but 1 over 1 plus x. So we're going to plug in a minus x into this familiar power series. So we'll have 3/4 times 1 plus not x, but minus x, plus not x squared, but minus x squared, plus not x cubed, but minus x cubed, etc. Okay, so this series will have negative signs popping up here and there. So we'll have 1 minus x, the negative x quantity squared will be a positive x squared, minus x cubed, etc. Okay. All right, now let's go to B. And B and D both kind of have an interesting little trick, I guess. And this will pop up on your WebAssign. So B is 1/4 times 1 over 1 minus x squared. And I just want to point out that this function cannot be rewritten to be, I'll do this in red. This cannot be rewritten to look like 1/4 times 1 over 1 minus something, okay? Because when you FOIL this out, you get 1 minus 2x plus x squared. So there's no way for you to actually rewrite this in some sort of like composition involving this 1 over 1 minus x squared that we have been using, or 1 minus x that we've been using. Instead, here's what we will note. This is actually 1/4 times the derivative of 1 over 1 minus x. So go ahead and check. You can check that the derivative of 1 over 1 minus x simplifies to 1 over 1 minus x quantity squared. So as long as you believe that, you can check. Then that means that we can differentiate that series, or that function's power series. I'm doing bad things. So let me finish this and then I'll say we'll have to go back and verify what we mean by this equals, and this equals. Okay, just so we have that noted. So this is where we'll be taking the derivative of the power series. Let me just write the power series of 1 over 1 minus x, which we know is 1 plus x squared plus x cubed, etc. So that will become 1 over 4 times 1 plus 2x plus 3x squared, etc. Okay. Similarly, D is 1/4 times 1 over 1 plus x quantity squared. And just like B, there's no way for us to rewrite this function as 1 over 1 minus something. So instead, what we can say is that this is actually the derivative of minus 1 over 1 plus x. Okay, so again, you should check that, but it's the derivative of that, and we know what that function's power series expansion is, don't we? So minus 1 over 1 plus x is the opposite of this little guy that we've already computed. So let's just write that down. 1 minus x plus x squared, and I should have a minus sign, minus x cubed plus x to the 4th minus so on and so forth. Okay, so we are taking the derivative of, let's distribute that minus sign through, negative 1 plus x minus x squared plus x cubed minus x to the 4th, and that derivative is 1/4 times positive 1 minus 2x plus 3x squared minus 4x cubed, etc. Okay, so this one also has an equal sign that we've got to be super careful with. This one, right? This is where we go from a function to a power series. And anytime you're going to say that a function is equal to a power series, you need to be careful about what interval you mean that on. So let's go back up to the top, because 1 over 1 minus x here, we know that that has a certain interval of convergence. What is it? It turns out that it is negative 1 to 1. Okay. So this purple equality is valid only for x values between negative 1 and positive 1. Similarly, you can check, but this guy's radius or interval of convergence will also be between negative 1 and positive 1. Then this equality here for part B, remember that the derivative of the power series has the same interval of convergence as the original. So this thing's interval of convergence is the same as this one, because we're just taking a derivative. Okay, and that's by our little theorem up top. So this guy's interval of convergence is minus 1 to positive 1. And just so that's, this interval of convergence implies this one by the nice theorem. And in that same way, the interval of convergence for C implies the same interval of convergence for D, also by the theorem. Alrighty, so everything we're doing is valid only for x values between negative 1 and 1. But now that we have all of this, we can go back to our original expression, add those pieces together. So we have 1 plus this a, okay, and a is minus 3/4 times that power series. Okay, plus b, and b is this power series, positive 1/4 times that power series, okay, plus c, which I think is actually going to have a negative sign, correct? Good, yes, c does have a negative sign. So this is the power series for c. Dang it. Okay, and then plus d. And here is what we computed for D. Okay, now there's a lot of similarity here and a lot of cancellation that's going to happen. In particular, these terms, the x terms, let me maybe highlight those in red. These x terms are going to cancel. These x cubed terms will cancel. So all of the odd terms, odd power terms in those two power series will cancel. And we'll end up with negative 3/4 plus 3/4 is a negative 3/2 times whatever's left over. 1 plus x squared plus x to the 4th plus x to the 6th. Okay, so that's the sum of A and C. Plus, we're also going to have some cancellation here between the B and D power series. This 2x and this negative 2x will cancel. There's a positive 4x cubed and a negative 4x cubed. They're going to cancel, and we'll be left with 1/4 plus 1/4 is a half times 1 plus 3x squared. Those 4x cubes cancel. We'll have a 5x to the 4th, etc. Okay, now let's go ahead and combine these. One last step, everyone. So we have 1 minus 3/2 plus a half. That's our constant term, okay? Now, what parts of our power series have an x? We don't have any x terms. So what about our x squared terms? We'll have a negative 3/2 and a positive 3/2. Ooh, that's odd, right? Oh yeah, okay. And then let's go to our x to the 4th term. So we have a negative 3/2 x to the 4th on the left-hand side and a positive 5/2 x to the 4th term on the right-hand side. Let's just do one more, just so we believe what's going on here. So on the left-hand side, we will have a negative 3/2 x to the 6th, and then the term that you can't see here has a coefficient of 7/2 x to the 6th. All right, so this pattern continues. We'll have negative 3/2 plus 9/2 times our x to the 8th term, etc. How is all this going to reduce? Well, our constant term reduces to 0. Our x squared term reduces to 0. Our x to the 4th term reduces to 1. Our x to the 6th term reduces to 4/2. That's 2. X to the 6th, 4. Negative 3/2 plus 9/2 is 6/2, which is 3. X to the 8th, okay? And this pattern will continue until you can eventually see that we're just adding up from n equals 1 to infinity the series n times x to the 2 times the quantity n plus 1 power. All right, man, okay, so I'm going to, I'll post it now. I'll just tell you, God, I kind of feel silly, but here's the deal. This is the correct power series. Let me show you the alternative, very sneaky, clever way that Dr. Hamidi showed me. He found the power series expansion. Instead, in case you've forgotten, this is the function we started with. Why don't you go ahead and pull an x cubed over 2 out, and then you would be left with 2x over 1 minus x squared quantity squared. Now, recognize that this is the derivative of something, okay? What's it the derivative of? Well, so we've got x cubed over 2 times the derivative of 1 over 1 minus x squared. So you should check that this derivative gives you that right-hand side. It does. All right, so then we've got x cubed over 2 times the derivative of, hey, this is a familiar looking series with a small transformation. That is 1 minus over 1 minus plug in x squared. to our familiar power series. And that gives you then the infinite series from 1 to infinity. And I'm going to write down the derivative of term by term, the terms in the power series 1 over 1 minus x squared. Okay. All right, so this is coming from the power series expansion. Of 1 over 1 minus x. So you can see that all we did is we replaced x with x squared in both of those expressions. Okay, great. Now differentiating term by term, that is done by the power rule, which we love. And that ends up giving you, once you FOIL this 2 through, you get 2n minus 2. That's the power. And then you reduce the power 2n minus 2 by 1, resulting in 2n minus 3. And then we're going to push this back in. And we have the series n equals 1 to infinity of 2n minus 2 all over 2 times x cubed times x to the 2n minus 3. And you see that a whole bunch of recombining can happen. The 2's cancel, you're left with n minus 1. And the cubed and the 2n minus 3 leave you with x to the 2n. Fabulous. Okay, so, yeah, hopefully that was mildly satisfying. That looks different than the series we have, but that's because its first term is 0. So let me write it like this. So if you plug 1 into the series here, you're going to get 0. So we could in fact start at n equals 2. And if we start at n equals 2, we can shift our series to start at 1 again, so long as we add 1 everywhere we see an n. And that is exactly what we got above. Okay, so either way you do this, this is the power series expansion you get for this guy. Now let's go back and just verify. We already said that this was valid for x values between -1 and 1. You can verify this by the ratio test. So if you want to see that, the ratio test would say, all right, what is the limit as n goes to infinity of our a sub n plus 1 term is this guy, but with n plus 1 plugged into n. So that would be n plus 1 x to the 2 times n plus 1 all over a sub n. And a sub n is just n times x to the 2 times n plus 1. And doing a little bit of algebra, you get that this is n plus 1 over n times the magnitude of x squared. Okay, so your x to the power of 2n plus 2 and 2n plus 1 in the denominator will whittle down to x squared in the numerator. And we need this to be less than 1 if we want this thing to converge. Well, that is true if and only if the magnitude of x is less than 1, which is true if and only if x is between the values -1 and 1. Whew. Okay, good job, everybody. This is a really, I think it's a very sophisticated mathematical concept. I think you have to give yourself time to really comprehend this and take your time in every step, not just to recreate the procedure, but to really understand why. For example, right here, that was a big step. That was a big step that we took. We just replaced a function with a power series, and that's only valid for certain values of x, okay? So just keep in mind that there's a lot of subtlety in every equality that you write down. There could be something there that you need to just be aware of, okay? All right,